Okay, so this is part two of bones and skeletal tissue lecture, and I'm having some technical issues, which is why we're in this view, and also why my webcam is not turned on because for some reason it's not working with the webcam on. So anyway, I'm going to continue like this for right now until I kind of figure out what's going on. But we've talked about some gross anatomy related to bones. And so now we're going to dive in and we're going to get a little smaller. So now we're looking at more, like the microscopic anatomy. Um, and one thing I like to keep in mind here is the fact that bone is very dynamic. So, bone is just constantly remodeling. It's not a static tissue. It's constantly creating new bone, and our body is constantly reabsorbing bone and breaking it down. And so we call this remodeling. And so remodeling is happening all the time. In fact, to the point that we actually develop an entirely new skeleton every 10 years of your life. So your skeleton completely replaces itself with new bone every 10 years. So we have some different types of cells that are active with this process. So one of them is going to be what we call an osteogenic cell. We also call this an osteoprogenitor cell. So this basically is the same thing. And this is a mitotically active stem cell. And so what this means is that this is a cell type that can differentiate into osteoblast when needed, basically, or when stimulated to do so. And so one of the areas that we see this is in the periosteum. So if you recall, we had, here's our long bone, right? And we had that periosteal layer that was covering, kind of the ends or the edges of the long bone, and it consists of two layers. Okay, so maybe this is our periosteum, and it had two layers, and the outermost layer was a dense, irregular connective tissue, and our inner layer, if we kind of highlight maybe an inner layer here, right up against the bone, consists of osteogenic cells. So I always kind of draw these little cells right here. So obviously this is not to scale. So we've got little cells there, and then we'd have the same thing on the other side. And so what happens is that when this bone is under stress, those osteogenic cells can differentiate into osteoblasts. And as you'll see in just a minute, osteoblasts are the bone cell that actively lay down bone or create bony matrix. And so in that way, they're able to actually deposit bone along the outside of the bone here, which is ultimately going to cause the bone to increase in width. And that's exactly what happens. But main thing being here is that in the periosteum and then also the endosteum, which we know if we draw a medullary cavity in here, that endosteum is going to be the membrane lining that medullary cavity, and it's got the same thing, so we're depositing bone from both the outside edge of the bone and then from the inside as well. But those are osteogenic cells, otherwise known as osteoprogenitor cells. Second cell type is going to be osteoblasts. And we kind of touched on this on the last slide, but these are kind of the immature bone cells. So these guys are actively mitotic. They actively create bony matrix. And it's important to note here that the initial bony matrix that they create is kind of an immature form of bone called osteoid. And it's basically collagen and protein. It's not as hard. It doesn't have the mineral salts that mature bone has quite yet. And what happens is osteoblasts are going to secrete bony matrix, and when they become surrounded by the bony matrix on all sides, they then become mature bone cells called osteocytes. So here's our osteocytes. So again, these are going to be your mature bone cells. These are cells that have these kind of long processes sticking out because they are responsible for monitoring the bone around them, and then they will signal chemically cells around them, either osteoblasts if they say they need to make more bone, and that's going to be their signal to them. They're going to say, hey, osteoblasts, make more bone. Or they are going to signal osteoclasts, which is a different cell type, and say, hey, break down bone, and tell them what to do. And this is basically maintaining levels of calcium in our body. And we do this through either increasing or decreasing osteoblastic or osteoclastic activity. I like to say that these osteocytes are basically like the boss, because they're basically like looking around, looking at the bony matrix around them and deciding what needs to be done. And then our final bone cell type is going to be osteoclasts. And these guys are specifically designed to do the job that they do. And so they are going to work at resorbing bone. And so they contain lysosomes with enzymes in them that dissolve the bony matrix, and both the organic part of the bony matrix, the collagen, and the minerals, so like the mineral salts. So they're going to contain enzymes and hydrogen ions that work to basically break down bone. And they've got this ruffled border. You can see that here on the edge, this ruffled border. That's going to increase the surface area that these cells are in contact with so that they're able to degrade the bone around them. So this is the cell type that breaks down bone. And again, it gets its signal from the osteocyte telling it that it needs to break down the bone. And so I asked the question here, so what happens in our body when osteoclastic activity is greater than osteoblastic activity? What happens if we break down bone, break down greater than our rate of building up bone? What happens there? So what happens is stress fractures or stress reactions. And you may be familiar with this, or maybe even had one. This is what it looks like on X-ray. And this is commonly what happens on X-ray, is the initial like stress fracture or stress reaction doesn't really show up. But what we see, you can kind of see this little kind of cloud of white around this bone. And that's what we call a callus. And that's a stage of bone healing. So sometimes the break or the stress reaction in the bone is not even enough to show up on X-ray, but what we can pick up a couple weeks later is the callus formation, which is basically where the bone is healing itself. But that's what happens if your rate of breaking bone down exceeds your rate of building bone up, and that's not a good balance to have. Okay, so in terms of microscopic anatomy, how is the bone arranged? Well, compact bone. So first of all, we have two types of bone. So two bone types. We're going to have compact bone, and we're going to have spongy bone. Okay, so all of this for right now is talking about compact bone. So with compact bone, it's very strong. Okay, and so it gives a lot of strength to the bones, and as a result, it's arranged in a specific way to allow it to provide that strength. Compact bone is arranged in what's called osteons, and we also call this the haversian system. This is our structural unit of bone. And so osteons run parallel to the long axis of bone. So if you had, you know, kind of your typical long bone here, osteons run parallel. So they're basically going to be running like this. So here would be our osteon. Okay, and then we're going to have our osteon next to it. So that's what we mean by parallel to the long axis of the bone. Like this line going through the bone would be the long axis of the bone. So it's basically groups of hollow tubes called lamella. And so if you look at them from the top, they're basically going to look like tree rings. So they look, if you've ever cut a tree down and you see the rings on the tree, that's what compact bone looks like. And what they are is each level is going to be a hollow tube. And so like this would be one lamella, this would be the next lamella, and this would be the next lamella. Okay, and if you stack them all up and look at them from the top, they basically look like this. They look like rings on a tree. And so what happens is that these guys have alternating fiber direction of collagen fibers. So the lamella are going to have collagen fibers that come in different fiber directions. So maybe this level, the fiber direction goes this way. Maybe this one, this lamella, the fiber direction goes that way. This one, it alternates. And so this provides a lot of strength. And because they're alternating fiber direction, they're going to resist twisting. Also, too, we have what's called interstitial and circumferential lamella. And so lamella that basically create part of an osteon, like if they create a full ring, they are going to be circumferential lamella. And the lamella that, I thought maybe I had a better picture of it, but the lamella that end up kind of in between complete osteons, so maybe here we might have a few rings that aren't completely part of an osteon, they would be the interstitial lamella. And you see that because the bone is constantly remodeling, and so it may not always remodel complete osteons. It might just remodel part of it, so you're left with kind of some interstitial lamella kind of stuck in between the circumferential. In the middle of each osteon, we have a canal, and that's what you see here, this kind of hole in the middle, and this is called the central canal. It's otherwise known as the haversian canal, and it runs in the middle of the osteon, and it's going to contain some interesting things. It's got blood vessels because bone is highly vascular, so we've got an artery and the vein. It's got a nerve running in it, and you'll find that this is a threesome that happens quite a bit in the body. So we're going to frequently have artery, nerve, and vein all, you know, kind of running together in structures. And so that's what we see here. That's what's contained in that central canal. And so that's running parallel to the osteon. And then we're going to have other canals. If we draw kind of our typical bone here again, so the central canals are going to be running this way because they're also running parallel to the long axis of the bone. Now we also have other types of canals that are running perpendicular to the long axis. So for instance, we could draw in another type of canal that's running this way. So it's basically connecting like medullary cavity to structures that are further out. And these are going to be called Volkmann's canals. Okay, or otherwise known as perforating canals. And so these run perpendicular to the long axis, so they're going to be going in this direction. And you can see them in the picture here, if you blow that up a little bit. So they're running perpendicular to the long axis. And they do the same thing. They're still going to carry blood vessels and nerves, but they're just going from medullary cavity out to the periphery of the bone. Okay, so within the lamella are going to be basically the rings of the tree Okay, within the lamella, we're going to have these little spaces, and these are little hollowed out areas, and these are called lacuna. And so these are basically little houses where the osteocytes are going to hang out and assess the bony matrix around them. So here we're going to have a lacuna with an osteocyte inside it. Here's a lacuna with an osteocyte. Now these osteocytes have long processes. So they're going to be kind of these cells, and they've got these long processes that kind of stick out away from them. And so they need to have a way to communicate with other cells that are around them. And they do this through this series of little passageways in the bone. So we would have kind of this passageway here that's going to connect processes from one osteocyte to another. And we call those little passageways canaliculi. So these are going to be small passageways like this in red here. This little canal would be a canaliculi. Okay, and so they're going to connect lacunae to each other so that the osteocytes can talk, and they also connect the central canal with its nerve and vein and artery to structures that are farther away from it. So if you look at images like this, these kind of lines that you see coming out from the lamella and from the lacunae are going to be the canaliculi, and that's how the cells communicate with each other. So we have cell junctions here, and I'm asking this question here, osteocytes are connected by which type of cell junction? If you have junctions like this, what type of junction would that be? So let's talk about what are our options of cell junctions. We've got tight junctions where we know we've got plasma membranes of cells, tightly embedded to one another. And this doesn't really look like that, it's described that way. We've got desmosomes, which are basically like Velcro, and they're found in tissues that resist shear, and that doesn't seem like it fits the bill here either. Or we've got gap junctions. So those are your three types of cell junctions. So this particular type of cell junction that we see here is going to be a gap junction. And so osteocytes are connected by gap junctions through the canaliculi. Okay, so here's our second type of bone. So spongy bone. So we had compact bone, that was what we talked about first. Now here's our spongy bone. So spongy bone is different. It's very poorly organized. It does not have osteons, but it does have some other structures contained within it. So basically the whole point of having spongy bone is because we need some space, okay? Because spongy bone is highly vascular, so we've got blood vessels traveling through it, and this is also the location for red bone marrow production, so we need to have some open areas to allow that to happen. So spongy bone is going to contain these kind of spines of bone called trabeculae. So they're kind of these bony spicules. Okay, so kind of a mesh of bones. They do have lamella, but they're irregular, so they're not shaped, like the tree rings like we saw with compact bone. That's not what we see here. They're very irregular. They do have osteocytes present, and they're still connected by canaliculi because they still have to have a way to communicate with structures around them. What's interesting too is that the trabeculae, that kind of open mesh of bony spines, is going to remodel based on stress. And we'll talk about that in a little bit. But realizing the main thing with spongy bone is that we've got these open spaces throughout the bone because blood is going to diffuse through them. And we also see that because of red bone marrow, we've got actually production of cells that's happening in this area. Okay, so here's your comparison of compact versus spongy bone. So like, this area here right along the edge, you can see that's going to be compact bone. And then this area here, this would be spongy bone. You can see all those open spaces. So this is going to be your spongy bone. Okay, in terms of chemical composition of bone, what do we see? We've got both organic and inorganic materials that make up our bone. Organic is going to be the softer material that we see. It accounts for about 35% of the total bone, and it's going to allow it to resist tension or stretch. Because it's softer, it's going to actually give bone a little bit of bend. And that's very helpful. So organic components of bone are going to be the cells that are present in bone. So here's our cell types that we've talked about. We also have our bony matrix, which we call osteoid, and that's going to be our ground substance and collagen fibers that we see in the bony matrix. In terms of inorganic components of bone, this is going to be the very hard part. So these are basically mineral salts, and in bone we call these hydroxyapatites. This is going to account for 65% of our bone, and the mineral salts are very, very hard. So they're going to allow the bone to resist compression, and they give bone its hardness. Bones basically grow in two different ways in our body. And so we can see bone development, and this is basically what we would talk about as fetal bone development. And this is going to happen in two different ways. One of them is going to be endochondral ossification. Ossification basically means creation of bone. Okay, so we'll talk about a structure ossifying or to ossify. Okay, and ossification means the creation of bone. Okay, how is bone created, or how do we end up with that bone? So here's one way that we end up with this process of ossification, and this is endochondral. So this kind of looks familiar, this chond, and we know that that means cartilage. And so that's what happens in this first method, is we have bone developing by replacing hyaline cartilage. And so the bone that results from this endochondral ossification process is called endochondral bone. Now we have a second method, and this is called intramembranous ossification. And so what happens here is that we've got bone forming from a fibrous membrane. Okay, and then the bone that results from this type of formation is called membranous bone. Okay, so this is what happens with endochondral ossification. Basically, a large part of the embryonic skeleton is formed out of a hyaline cartilage template. Okay, and so this basically forms a template or a pattern initially made out of hyaline cartilage that bone can now come back afterwards and replace. And so starting at 8 weeks gestational age, the body starts to replace that hyaline cartilage with bone. And this happens with all bones in the body below the skull except the clavicles. And we'll talk about those in just a minute. So skull and clavicles are kind of our outliers here, and also mandibles. But what we have is two ossification centers. So the first one is going to be a primary ossification center. And what we see here is that in the shaft of the long bone, in the diaphysis, we start to form a bony collar. And you can kind of see that here and here. And what we end up having is a deterioration of cartilage on the inside of the shaft. And that ends up eventually developing into our medullary cavity, because this cartilage here deteriorates and just kind of goes away, and leaves us with a space. And so that's going to end up becoming our medullary cavity. So we're going to have a blood vessel, and we call this the periosteal bud, and that's going to travel in and pervade throughout the interior of this long bone. And it's basically supplying good blood supply to that area, and starts to create bony tissue in the diaphysis of the bone. So what we end up having here is this initial creation of spongy bone and then replacement with compact bone through our primary ossification center. So our diaphysis is going to be replaced by bone. Cartilage is going to be replaced by bone in our primary ossification center. So that's going to form the shaft of the long bone, or the diaphysis, and also as a result the medullary cavity forms. And then we've got our secondary ossification centers, which is going to be what happens in the diaphyses of the bone. And so we have the same thing there. We have kind of this this blood vessel that's going to come in and supply that area. And this is now going to be our secondary ossification center. So this is kind of the second part. And the secondary ossification center is going to be responsible for ossification of the epiphyses. Okay, so they're going to turn to bone. And what you have left, and this is after birth, is a layer of hyaline cartilage or growth plate between the diaphysis and the epiphyses. So you can see that here and here. So that's going to be your epiphyseal plate. In terms of intramembranous ossification, you're going to see that this is basically forming from a connective tissue membrane that covers the outside and then is eventually replaced by bone. And so that's the process that happens here. We see this in the bones of the skull. You also see this in the mandible, and you see this in the clavicles. And so all of these guys here are going to be intramembranous ossification. The rest of the body is going to be the endochondral ossification. And then we still have long bone growth after birth. So after you're born, your bones grow. You grow taller until adolescence, and then it stops. But we have two different processes where this happens. And the first one is we've got bones that basically grow in length. So we're going to start with, kind of shorter bones, and then they're going to grow and become longer. And you see that that's what happens as you grow when you're a kid and teenager. Basically what happens with this, when bones grow in length, we call this interstitial growth. And so that's bones growing, longer. And then here we've added some growth, some length to our long bone. So basically what happens there is that we've got this epiphyseal plate, that's this plate of cartilage, hyaline cartilage, that's dividing our epiphysis from our diaphysis. And what we see there is that we have cartilage cells in that epiphyseal plate that are proliferating. They're basically dividing and laying down more cartilage. So that would be this area up here. They're proliferating, laying down more cartilage. Underneath that layer, we've got this hypertrophic zone, and these older cartilage cells are becoming bigger. So here we've got larger hypertrophied cartilage cells. Underneath that, we've got a calcification zone, which means that the cartilage, those chondrocytes, are basically dying, and the matrix in that area is becoming calcified. So that would be, so let's say 1, 2, 3. the fourth layer is going to be the layer underneath that, and that's going to be our ossification zone. And anytime you see the word ossification, you know that that means something's turning to bone. So in this area here, we've got bone. Now it was cartilage, and now it's ossified, and so now it's being replaced by bone. So basically what we're doing is we're pushing the epiphyses away from the diaphysis. And we would do the same thing here. We're going to push this epiphysis away from the diaphysis. And in that way, we're gradually adding new bone. So this epiphysis is going to get pushed away up here, and then the next time it's going to get pushed up here, and this growth plate is going to continue to move up. And that's how the bones grow in length. Until the growth plates close. And after puberty, the growth plates stop reproducing. The cartilage cells stop undergoing mitosis, because we know that that's what happens when chondrocytes become mature. And basically it just stops. So once this process stops, your long bone growth has stopped. And this typically happens in late adolescence. And you're left at that point with just a line, in the bone between the, I'll draw it down here, between the epiphysis and the diaphysis. And that's just going to be an epiphyseal line. So that means that the growth has stopped. And that's what you would see in an adult bone. Now, on the contrary, we can continue to grow our bones in thickness even after adolescence is over. And so we grow bones in thickness by a process called appositional growth. And this is the growth that happens when we have those osteoblasts, initially those osteogenic stem cells in the inner layer of the periosteum that differentiate into osteoblasts as a result of stress. And it makes our bones, get wider, because we've got these cells that are lining the periosteum here. And when they increase bone deposition in that area, the bone is then going to get wider. And so this is in response to stress that this happens. And this is kind of a remodeling type of thing. But bones can grow by thickness throughout your life. And that's why it's important to continue to stress your bones so that you can continue to make them stronger. Now, it is important to note that you're adding bone to the outside of your long bone here, but you've got osteoblastic activity here on the outside. What you also have is osteoclastic activity towards the inside. Bone is being resorbed there, because what we don't want to have is really thick, heavy bones. We want the bones to get wider, but as a result, the medullary cavity enlarges as well, because otherwise our bones would get really, really heavy, and then they wouldn't be quite as functional. This is showing you here, this is a image, this is X-ray, showing you growth plates around the knees. It kind of looks like it'd be a fracture line, but you know that it's not, because of where it is and how this looks. But the line that you see is a epiphyseal plate, because cartilage is not radio-opaque. So it just kind of shows up as like a space between the bones. This is what it would look like if you had a fracture, even like an offset fracture of a growth plate. And so this is one of the risks that happens when kids break bones, is that this is an area of weakness, actually. It's actually a joint, but it's a little bit weaker than the rest of the bone. And so depending on, the injury and the force, kids can often fracture their bones at their growth plate. And what's problematic about that is that sometimes you can have kind of a premature closure of the growth plate if it undergoes trauma. And so it can stop growing, and kids could theoretically be left with one arm or leg that's longer than the other, because the other one that wasn't injured continues to grow. But it doesn't happen very often, but when it does, it can definitely be problematic.